Assalamu alaikum, dear student. This is lecture number 3 of week 3 and we are continuing the chapter number 2, pressure and fluid static, and the topic we are going to cover today are the hydrostatic force on a plane surface and pressure prism. So let's see what we are going to study under the heading of force on a plane surface. Hydrostatic force on a plane surface means when a surface is submerged in a fluid, forces develop on the surface due to the fluid. Determination of these forces is important in the design of storage tanks, ships, dams, and other hydraulic structures. For fluid at rest, the forces developed on the submerged surface are due to the fluid pressure and are perpendicular to the surface. So we all know these forces are perpendicular to the surface regardless the surface is horizontal, vertical, or and making any angle with the vertical or horizontal surface. For gases, pressure is uniformly distributed all over the container. Therefore, due to gas pressure at any particular surface boundary of the container, the resultant force acts at the centroid of the surface. For liquid, the pressure is not uniform. It increases with the depth. Therefore, due to pressure at any particular surface, the resultant force does not act at the centroid but act at the point below the centroid of the surface. So it is very clear, if any surface which is submerged in a liquid, if the applied force is uniformly distributed on the surface, in that case the resultant force act at the centroid. If the distributed pressure on the submerged surface is non-uniform, then the net resultant force will act below the centroid of the surface. Let's consider a normal case for the horizontal surface, such as the bottom of a liquid filled tank. So here you can see in the picture, this is the bottom surface and this is uniform, flat, and this is a vertical surface, but at the moment we are focusing on the bottom surface, and we can see the distributed pressure on this surface is uniform. So in that case it is very easy to calculate the net pressure acting on the surface and also to find out the location of the net resultant force. So in that case we know the equation. The net resultant force is equals to pressure acting on a surface area. So A is the area where the net pressure is acting. So force is equals to pressure into area, and that is Fr is equals to P naught plus gamma H into A. P is the atmospheric pressure which is acting on the surface, or P naught could be the any initial pressure which is acting on the free surface. So here this is the net resultant force. Since the distributed pressure on the uniform surface is uniform, therefore the net resultant force will act at the centroid of the surface. So here the atmospheric pressure acts on both sides of the surface, therefore the unbalanced force act at the bottom of the liquid filled open tank is gamma HA. So here means this is the atmospheric pressure, since this is the surface. So atmospheric pressure acting here and atmospheric pressure acting here, they are cancelling each other, okay, because the pressure always acting perpendicular to the surface. So here the direction of pressure is in this direction, okay, from the bottom, and at the top the direction of the atmospheric pressure is from the top. So these two forces, these two atmospheric pressures which are acting on this surface are cancelling each other. So only net unbalanced force, which is the hydrostatic pressure, due to the weight of the fluid, that is rho g HA. So this is height of the column, and this is the area at which the pressure is acting, and this is the weight density of the fluid. Since the pressure is constant and uniformly distributed over the bottom, the resultant force acts through the centroid of the bottom surface area. Let's move on to the next case. Here now we are focusing the side surface, not the bottom surface. At the side surface we can see the pressure is gradually increasing, because the hydrostatic pressure is directly proportional to the height of the column of water. So as the column will increase, as the depth of water will increase, the hydrostatic pressure will increase. We can see in the sketch the pressure is gradually increasing, okay, as we are going down the pressure is gradually increasing in the case of the side wall. So here the pressure distribution is non-uniform. So in that case the net resultant force acting on this surface is not at the centroid, it will be below somewhere in the centroid. But how below, how we can calculate the magnitude of the force, and how we can calculate the location of the net resultant force, that we will see in the next slide. So here the pressure on the side wall of the tank is not uniformly distributed. We will learn how to determine the resultant force and its location for the situations such as one discussed here, okay. So let's move on to the next slide. So consider more general case as a vessel of a inclined side wall. So here let the inclined plane intersects the free surface at O and makes an angle theta with the free surface. So here is the inclined plane, okay, which is, if I draw a line parallel to the surface which is intersecting the free surface, this is our free surface. Free surface is a surface where there is no shear force when the fluid is at rest, and there is only one force which is acting on the free surface, that is the normal pressure. So here at point the plane is intersecting and it's making an angle with the angle theta with the free surface. If O is the origin of x and y coordinate system and y is directed along the inclined surface, so this is our x-axis. Here you can see x, this is our x-axis, and this is our y-axis, okay, which is parallel to the inclined surface. So this is our y-axis. So the area can have an arbitrary shape as shown in the figure. So this is the area at which the pressure is acting. This arbitrary shape can be circle, can be rectangle, can be square, can be triangle, and can be any regular and irregular shape. So let's consider a small area dA, and the force acting on this area is dF. Okay, the force always acting perpendicular to the surface. So what is our objective? Our objective is to determine what is the net resultant force acting on this surface and what is the location of the net resultant force acting due to the hydrostatic pressure. Consider a small area dA on the arbitrary surface. The reason of considering a small area, because the area is irregular and the force acting on this small area is dF. So if we integrate this small force over this entire area, so we can determine the net resultant force acting on this surface. So because of that, we have considered a small area which has a distance x from the x-axis and y from the y-axis as shown in the figure. And the centroid of this surface, which is indicated with the letter C, and it is at the distance of xc and yc from the axis as shown in the figure. This is the distance xc from the x-axis and this is the distance yc from the y-axis. And the position of net resultant force, since the pressure is non-uniform, so the location of the net resultant force always below the centroid. Okay, so the position of net resultant force is xr and from the y-axis is yr as shown in the figure, and net resultant force is indicated with the fr, and it is making at height h c from the free surface, and the small force acting on a small area, it has a distance h from the free surface. So next, consider at a given depth h, the force acting on any differential or a small area dA is dF. Force is equals to pressure into a small area. Small force is equals to pressure into a small area, and pressure, we know that the hydrostatic pressure, we know that is equal to gamma h. Okay, so we replace this P with gamma h into dA. So, and is perpendicular to the surface, so this force is always perpendicular to the surface. To find out the magnitude of the net resultant force, it can be found by summing these differential force over the entire surface. In equation from this, so Fr will be, I take the integration both sides, so Fr will be equal to, we are going to integrate this small force over the entire area A into gamma h into dA. Okay, so since it is the function of area and area is definitely is equals to x and y, so we are going to replace this h with x and y dimension. So h we are going to replace with y sine theta. How h is equal to y sine theta? Let's go back to the previous slide. So this is the distance h. Okay, the small area we consider, it is at height h from the free surface. So this is h and this is what? This is y and this is angle theta. So this is perpendicular, this is hypotenuse, so h is equals to y sine theta. Yani sine theta is equals to h over y, and h is equals to y sine theta. From here we can consider a small triangle and we can calculate this. So we replace h with y sine theta, and then finally Fr is equals to theta is constant, specific weight of the fluid is constant, and the only variable is y. Okay, so y dA over entire area. So we can write down the integral of area over area. Y dA is the first moment of area with respect to x-axis. Okay, so we can write down y y dA integration of over area is equals to yCA. Okay, we can, this is the first moment of area and we can write down in this form. So we are replacing this factor with yCA. Okay, so we are replacing y dA integration over area with yCA. So let's move on. So we have replaced this, where yc is the y coordinate of the centroid measured from the x-axis which passes through the origin. So thus the resultant force Fr can be written as Fr is equals to gamma yc, yani gamma sine theta was remain there, so we replace that with ayc. So because of that, the net resultant force will be equal to gamma ayc sine theta, or simply we can replace yc sine theta with hc. So Fr is equals to gamma hc into A. So the magnitude of the resultant force will be equal to Fr gamma hca. So we replace yc sine theta with hc. How it came? So from here you can see this is your hc, and from here the net resultant force, the distance from net resultant force to the O, okay, from x-axis is yc. You can see from here this is yc from here to here. So yc, you can make a triangle. Yc is the hypotenuse, hc is the perpendicular, and theta is the angle. So hc will be equal to yc sine theta. So we replaced yc sine theta with hc. So this is the net magnitude or net resultant force acting on the surface. Okay, so where hc is the vertical distance from the fluid surface to the centroid of the area. So the above equation indicates that, so what we achieve, what this equation indicates, the magnitude of the resultant force is equal to the pressure at the centroid of the area multiplied by the total area. So this gamma into hc is the pressure, okay, multiplied by the area. So this is the factor of pressure and this is the area. Second, the magnitude of the resultant force is independent of angle theta. You can see there is no angle theta here. Okay, so that means the net resultant force is independent of theta. Okay, and depends only on the specific weight of the fluid. Okay, it's depending on the specific weight of the fluid, and it also depending on the depth of the fluid, and it's also depending on the area of the surface at which the fluid is acting or the pressure is acting, and the total surface area and the depth of the centroid of the area. So now we are going to determine the location of the resultant force. When an area is subjected to a pressure, a point in the area exists through which the entire force could be concentrated with the same external effect. This point is called the center of pressure. If the pressure is uniformly distributed over an area, the center of pressure coincides with the centroid of the area. In the case of non-uniform pressure distribution, the resultant force acts at center point XR, YR located below the centroid XC and YC as shown in the figure that we have discussed previously. Let's see how we can find out the location of the net resultant force XR and YR. To find out the location of the net resultant force XR and YR, so normally we consider movement. Whenever we would like to find out the location of the force, so we take moments. So to work out XR and YR, taking moments of FR about x-axis and about y-axis, that is, moment along x-axis is equals to FR into YR, and FR can be replaced by DF, the small area. Okay, the My is equals to FR into XR, and it can be written in this form. Okay, so DF, the small area that we have previously discussed, DF is equals to gamma H into dA, and later on we replace this with gamma y sine theta into dA. So in the same way we can write down FR is equals to, that we have derived already, gamma HC into A, and then we replace HC with YC sine theta, so it will become gamma YC sine theta. We replace HC with YC sine theta, and H we replace with Y sine theta. Now we are going to insert the value here for FR in the form of theta. So in the case of Mx, it will become Y will become Y, remain Y, and we replace FR with gamma Y sine theta dA, it is here, and the same X will remain X here, and DF will be replaced with gamma Y sine theta dA. Now we simplifying this. After simplification we end up with, in the next step, what we actually have done, this is FRYR, and our objective is to find out YR and XR. So here we replace FR with gamma YC sine theta A. We replace this FR with this value multiplied by YR is equal to, here the gamma and sine theta are constant, and Y and Y will become Y square into dA, and this will be integration over area A. Same thing here, we replace FR with this value, and it become like this, the gamma YC sine theta A into XR, and here also we replace DF with the above value, and becomes gamma and sine theta was constant, so XY dA. So here there is a term integration of y square, so here we simplified that, sine theta and sine theta is cancelled, gamma and gamma is cancelled, so from here YCA YR is remaining, and from this side integration of y square into dA. Same thing here, sine theta and sine theta is cancelled, gamma is cancelled, so YC into A into XR is equals to integration of XY into dA is remaining. So we simplified it. Our objective is to determine YR and XR, so we separated from other factors, so YR become integration of y square dA over YCA, and XR is equals to integration of XY dA over YCA. So the factor integration of y square dA and integration of XY dA, it has a special value. So let's move on. The term y integration of y square dA is called second moment of inertia with respect to x-axis, located at the intersection of the plane, and the free surface denoted by Ix. The term XY dA is called product of inertia about x and y axis denoted by Ixy. So we replace this term this term and this term with Ixy, and this is replaced with Ix. Okay, so here Ix and Ixy are the moments about x and y axis. These moments can also be converted to the moment about the centroid of the plane using the parallel axis theorem. By using the parallel axis theorem, these moments can be converted into moment about the centroid. So we can write down Ix is equals to Ixc plus Ay square c, and Ixy can be written as Ixyc plus Axcyc. So now we are going to replace these terms, this term with this value and this term with this value. So we inserted this value in the previous equation, so it become xr is equals to Ixy plus Axcyc divided by Yca, and yr will become Ixc plus Ay square c over Yca. So we simplified it, and finally we end up with xr is equals to Ixyc Yca plus xc, and yr is equals to Ixc Yca plus yc. So here you can see that in the above equation, Ixc and Ixyc are the moment with respect to an axis passing through the centroid of the plane. Centroidal coordinates and moment of inertia for some common areas are given in the figure. Okay, for common geometry we have some standard moment of inertia which are given here. If you have a rectangular shaped plane surface, then the moment of inertia of along x-axis and y-axis about the centroid is given here. If it is circle, it is given here. If it is semicircle, it is given here. If it is rectangle, so it is given here. If it is a quarter circle, it is, all the values are given here. So whatever is the shape of the surface, accordingly we can take the moment of inertia from this figure. So these two equation indicates that, okay, we can physically see that when the distributed pressure is non-uniform, so the net resultant force will always acting below the centroid. So here you can see that this is the distance from the centroid xc plus some value, and here you can see that this is the distance from the centroid yc, and plus it has a plus factor. So that means the net resultant force will always act below the center. Let's see a practical problem that make our concept more clear. So here the problem is the 4-meter diameter circular gate of figure as it is mentioned below is located in the inclined wall of a large reservoir containing water. The specific weight of the water is given. The gate is mounted on a shaft along its horizontal diameter. For a water depth of HC from the centroid is equal to 10 meter above the shaft, determine the magnitude and location of the resultant force exerted on the gate by the water. B, the momentum that would have to be applied to the shaft to open the gate. So here we have to determine three things. Number one, first we have to find out the net resultant force, that is Fr, and second we have to determine the location of the net resultant force Fr, and third we need to find out a moment, that is required to open the gate against the hydrostatic force. So we know what is the formula to calculate the net resultant force. So net resultant force we know that is equal to gamma hc into A. So what is gamma hc? So gamma, it is given 9.80 because the fluid is water. So the gamma is given 9.80 kilonewton per meter square. Hc, what is Hc? Hc is given, that is 10 meter from here to here. The area we have to calculate since the geometry of the gate where the hydrostatic force is acting is circular. So what is the area of a circle is pi r square. So let's move on. Here you see the net resultant force is equal to gamma hc into A. Gamma is equals to 9.8 into 10 power 3 and hc is given 10 meter and A is equals to 4 pi. So pi r square. So the diameter, the area, the radius is 2 meter. So when you make it is going to be pi r square. So when you multiply all them together, so we will end up with 1.23 meganewton. So the net resultant force which is acting on the gate is 1.23 meganewton. Our next step is to find out the location of the net resultant force. So what is the formula of the location of the net resultant force? XR is equal to IXYC over YCA plus XC. YR is equals to IXC over YCA and plus YC, that we derived previously. So that is, you see, so XR will be away from X distance and it will also away from the distance from the centroid in Y direction. So these two are known, XC and YC are known, that we can say, because since HC is known, so angle is given, so we can easily calculate what is XC and what is YC. So it is 10 over sine 60 degree, that is YC, and in the same way we can calculate XC. So in the above two equations, three things are unknown. Ix, YC, IXC and XC is unknown. YC is known, area is known. So let's see how we can find out the IXYC, IXC and XC. The XR, the XC, the XC going to be 0, okay, or XR going to be 0 because it is acting on this center line. So from this side and this side, since the pressure is uniformly distributed, so because of that the center of pressure in the X direction will be equals to 0. It will not be away from this point. So here we can say the XR is equals to 0 because the pressure distribution across the axis is balanced. So it is going to be 0. Since the area is symmetrical and the center of pressure must lie along the diameter AA. To obtain YR, we have from figure 2.8. So go back to figure. So here, so this is 0, the whole factor is 0. Now only we need IXC. So let's go back to the previous picture here. This is the circle, okay, when the gate is a circular shape. So here is IXC and IXC is equals to pi r4 over 4. So we can calculate now the IXC is equals to pi r4 over 4. So we know that R is equals to 2 meters. So finally we end up with 11.6 meter. So in this way we can say that the distance along the gate below the shaft to the center of pressure. So YR minus YC is equals to 0.866. Okay, so now these are some more practice questions that you can do it at home. So let's discuss the other content of today, the pressure prism. So pressure prism, what exactly it is? So here we can see that consider the pressure distribution along a vertical wall of a tank of width B. So consider this is the width in a 3 dimension. If you can see it is appearing as a prism. Okay, it is appearing as a prism. This is the width B. This is the maximum pressure which is acting at the bottom, because this is the maximum height. So this is gamma into H, and then as the height is reducing, the pressure is reducing, and at the top it is equals to 0. So from 0 to maximum it is making a triangle, and it is along the depth the triangle is continuing, so it's giving you a shape of prism. So the pressure distribution is like a prism, so it is called a pressure prism. Okay, in figure B, this is the figure B, shows the 3-dimensional representation of pressure distribution. Okay, the base of the volume shown in figure B is the pressure area. Space is the area of interest. Altitude at each point is the pressure. The volume shown in figure B is called pressure prism. The resultant force acting on the rectangular area. Okay, this is the rectangular area. So the resultant force on the rectangular area is equals to A is equals to B into H. So this is B and this is into H. So this is the resultant area. So we know that the net resultant force in case of a non-uniform pressure distribution, that is equal to gamma HC into A, and we replace HC, what is HC, from the centroid, that is height H, and it is H by 2. So it is going to be H by 2 into area. So finally we can write down gamma into H by 2 into B into H. So this above the above equation shows that the resultant force acting on the surface is equal to the volume of the prism. So what is the volume of the prism? This is the volume of the prism. That means what is the total area of the cube is length into width into height. If you divide by 2, so you will get the area of the prism. So this, what exactly it's showing, the volume of the prism is basically indicates the net resultant force acting on the surface. This is another way to calculate the net resultant force by using the technique. So if you have length, width and height, if this is basically the special case of the case we have discussed before. So here you can see this is the case. If you take theta 90 degree, so this plate will going to be straight vertical like this. Okay, so this is the special case of the pressure prism. Okay, so the resultant force must lie on the centroid of the pressure prism. Okay, so in that case resultant force act on the centroid of the pressure prism, which is located along the vertical axis of symmetry of the surface and at distance of h by 3 above the base. Okay, so this is basically the standard. Okay, so you can find, if you know this technique and you have a case like this, so straight away you can find out if you know the length, width and height, so straight away you can find out the net resultant force, and also you can find out the location of the net resultant force by using this technique. So here is an example. This we will solve it in the next lecture. Okay. Assalamu alaikum wa rahmatullah.